Thank you all very much for coming along to the rest of these seminars. I'm really happy to introduce Dr. Jon Carey. Jon and I go way back to our time we left together in New Zealand. But Jon did his undergraduate through his PhD at Durham University, slightly overlapping with industry jobs.
Yeah, that's right. You're part-time PhD student. Yeah.
But then went to New Zealand from there.
Yeah.
No, something in between.
No, yeah.
Went to New Zealand.
Pretty soon after.
Where he worked with the landslide research group in natural hazards division, and has recently returned nearly 2 years ago now to work as associate professor at the University of Dublin, continuing to look into hazard research. So really great to have you here, Jon. Thank you very much for coming in your time. Take it away.
Yeah, right. Thank you very much, and thank you very much for having me. Today I'm going to talk about some of the work I've been doing in laboratory simulations, shallow subduction zones, and landslides. So yeah, as Dave said, I'm an associate professor in applied geosciences at the University of Birmingham. So yeah, from 2002 to 2012, I worked as an engineering geomorphologist in industry, a company called Halcro, which has now been bought multiple times, but now Jacobs. And during that time, I worked on a lot of large landslides around the UK. Also worked in places like Hong Kong, looked at things like route corridor assessments and those kind of big projects. And during that time, I did my PhD part-time, looking at the mechanics of landslides, the mechanisms that cause landslides to fail. And I worked mostly on the Isle of Wight on Ventnor. So at the end of that year, I moved to New Zealand for just over 10 years. And I worked as an engineering geologist in the team there, really working on landslide hazard and risk. So I worked on things like the Canterbury and Kaikoura earthquakes. We looked at a lot of the rainfall-induced landslides that happened in New Zealand over that time, which were quite regular. I also moved into working on submarine landslides, which are quite an interesting area. And then, I guess, working in a big tectonically active place, we started to see the links between landslides and subduction zones, and started to get really quite interested in subduction zone behaviour. So that's kind of where I've started to go. So my main motivation for this is really, if we look at landslides globally, so one of the papers that's cited quite often is this paper by Frood and Petley. We see that the global fatalities are really high from landslides. So we have something like 56,000 fatalities between 2004 and 2016. You can see that from the graph, from the figure of the globe there. These happen in really kind of tectonically active, very wet locations you'd expect with high terrain. So there's a certain kind of countries that are really badly affected. But even if you look at the UK, we have over 18,000 landslides in the national database that's held by BGS. So we certainly have landslide problems here, although not as severe. And the picture on the left is just showing the kind of impacts that they have. They impact property, infrastructure, the environment, obviously, as well as fatalities. And a clear thing is that with the climate change and the change in environment and the way that weather patterns are changing, we're expecting landslides to become more prevalent and increase. So the impacts of these things are only getting worse with time. So we really need to understand how these things work. And then I guess the other thing I'm really interested in is subduction zones and the patterns of movement. And what we've been seeing as we've got better at monitoring subduction zones is that they have really interesting patterns of movement. So they slip in different ways, and their patterns of movement look very similar to the patterns of movement that we see in the really big deep-seated active landslide complexes. So we see these behaviours that are quite similar. And I think that makes sense, right? Because the physics that's driving these, we're looking at fine-grained sediments moving on shear surfaces at certain kind of angles. So you'd expect the physics to be broadly similar. So I think landslides are a really good analogous thing that we can look at, that we can study really quite well, that would really help us understand subduction zones. And if we can understand how the patterns of movement change over time, and certainly when we get really rapid accelerations in these kind of systems, that may help us understand really big earthquakes. So that's kind of what I'm trying to pull together today, is kind of my research across these areas. So if I could kind of sum up my main research aim, it's really to try and understand really landslide and shallow fault movement mechanisms. And I'm particularly interested in responses to pore fluid pressure and earthquakes, so seismic loading. And what I do is I use advanced shear testing to basically replicate the stress conditions in shear zones in a range of different environments, and then try to basically replicate the stress states that we think are operating when we have these events, and then trying to look at what happens to the materials, how they deform, how they behave. So the kind of testing I do is, the one on the left here is a tracks of cell. So I've used tracks of cell type testing, but a lot of my focus has been using direct shear. So the two machines, the central one and the one on the right hand side, are basically back pressure shear boxes. The one in the center is a dynamic back pressure shear box, so we can basically replicate seismic loading, simplified seismic loading, and the red one on the right hand side, that's a high pressure shear box, which has got, again, high pressure back pressure shear box. So we can look at static conditions and pore fluid pressure changes, but at much higher pressures, much higher stresses, so we can get better kind of deeper conditions into landslides and subduction zones. So this is just how these systems kind of work. So picture on the left here is just a simple kind of cartoon of a slope, and we can take a sample from a landslide shear surface, or a slope where we think a landslide shear surface might form. And we can put it in the shear box. And in this shear box, it is based on a kind of standard direct shear device, where we basically put the sample into a cell, and that cell is then in a vacuum. We fill that with water, so we can saturate the sample completely, and we can build a pore fluid pressure around it. And we have a volume control that controls that pressure. So we can basically build up pressure, water pressure on the sample, and we can measure the pore pressure response as best we can at the base of the sample. So that as the pore fluid is moving from the back pressure, we can look at the pore pressure of the sample. And then with this machine, what we can do is we can control the horizontal strain, the displacement rate, and the vertical displacement rate, but we can also control the loading, so we can control the stresses. So what we can effectively do is we can build a stress state in the ground, and then we can then basically change the stress to represent what we want to happen. So if we want to build pore fluid pressure, we can hold shear stress and normal stress constant, and we can push up back pressure until we get failure, or we can hold our water pressure constant, and we can dynamically change the stresses to replicate earthquakes. So this is a really good device to kind of look at those kind of processes. So some of the research that we've been doing, or I've done over time, is trying to understand certain things about landslides that we still don't fully understand. And one of the things that we've started to look at early on was how do landslides creep to failure. And this is really interesting because most landslides either happen for some kind of stress change, usually something like big rainstorm events, change in groundwater pressure, some kind of earthquake, and we get a landslide response. But in some cases, landslides seem to happen without any discernible trigger. This is an example from New Zealand. This is Mount Cook, Rocky Mount Cook, and this was the time when basically the top of the mountain fell off. So the highest mountain in New Zealand is not as high as it used to be, and this happened without any real discernible trigger. There was no rainfall event that seems to trigger this. There's no real earthquake that seems to trigger this. This just kind of fell off on its own. So really trying to understand how these shear surfaces in landslides develop through time, and how can some slopes fail without any discernible trigger. So to understand this, we need to kind of understand the concept of progressive failure, which is not a new concept. This is kind of thought about in the 50s by Carl Tazagi, and then conceptualized into like a progressive failure model by Bergeron in the late 60s. And this is the idea that for a slope to fail, it has to go from an intact condition to a stable condition to an unstable condition. So we have to go from some kind of intact system to a system that's damaged. So for that to happen, if we think of a landslide failing or a material failing at a factor of safety of 1, we have to go from a condition of above 1 to 1. And for that to happen, something has to change in the material properties, right? So something has to happen, and we think that must be deformation. So as a consequence of that, we should see some pre-failure deformation before we see something failing. And this is this idea that we have some kind of progressive creep from before we become kind of unstable, if you like. And that deformation drives a situation where we eventually get a failure, and then we get kind of post-failure behavior over time. And then this idea was then looked at in more detail in laboratories, and probably the most famous is the Barnes work in the 80s, which basically showed that if you creep a material to failure, you can see these different patterns of movement, and we get like primary creep initially as we start to deform something, then we get this secondary creep failure, secondary creep behavior, and then eventually we end up with tertiary kind of acceleration to failure, this three-phase creep, which is very well understood. So we're obviously getting this progressive deformation patterns to failure. And then so with this idea, people have then looked at this and said, well, we can use this to start to try and predict the timing of failure if we understand the patterns of movement, how we can do that. And this was kind of done by Sato in the 60s, and then later by Kutizonu, who started to look at this in actual landslide movement systems. And what they basically showed was if you take the surface displacement, the patterns of movement that you see in a landslide, and if you plot that as velocity rather than displacement, and then plot that as the reciprocal, 1 over velocity, with a landslide that's accelerating failure, you should get a linear trend, and that linear trend is going to tell you the time at which it's going to be really accelerating fast. So obviously, when you get to one over velocity of 0, you've got kind of infinite acceleration theoretically. So that linear trend is giving you some indication of when a landslide is going to fail. And this has worked really well for some landslides, but it's obviously works really well retrospectively, which is not very helpful when you're trying to predict landslide. Next one. So we've looked at this and tried to see if we could link this to the ways that actual materials deform these patterns of movement. And what was found by Dave Petley in the early 2000s was that actually, if you look at landslide movement patterns, they usually fall into 2 different categories. The one at the top here is an asymptotic trend in 1 over velocity. So this is like acceleration to a constant displacement rate. And then there's a group that kind of produces a linear trend in 1 over velocity. So if you do experiments in triaxial cells where you try and replicate those conditions by basically pushing pore pressure in, trying to create like a rainfall-induced landslide in the laboratory, what we found in almost all cases was when you've got ductile deformation, where you didn't get the formation of a singular shear surface, your 1 over velocity plot basically was asymptotic. And then when you got a brittle failure with a crack propagation and a singular shear surface forming to failure in brittle materials, you've got this linear trend in 1 over velocity. So I think what this tells us is, the mechanism in which the deformation is happening in your shear zone really dictates the behavior and the movement patterns that you see in the landslides. So that's a really useful thing that we can start to see that the material mechanics are really driving the way that the landslide moves. So from this, we wanted to understand basically how we can get an intact slope to progressively fail. So what we did was we set up a really long slow creep test in a triaxial cell. So this went for nearly over 500 days. So it was left on for a very long time. The university wasn't overly happy with us doing this because of obviously IT issues and things, but we left it running for this long. And what we effectively did was we were pushing up pore pressure, trying to get some kind of deformation response and get some kind of strain response. And once it started to deform, we'd hold that pore pressure constant until that deformation stopped. And then we'd slowly increment the pore pressure back up to try and get it creeping again. And what we're trying to do is see if we could get the failure to happen at constant stress. And you can see by the time we got to the last 81 days, we've got a situation where we've got a constant stress state being applied. And what we saw was basically that this kind of progressive pattern to failure. So what we could see was we saw this kind of stepped pattern and then this kind of sudden acceleration to failure. So what we think we're showing is that, what's effectively happening over time is that as you get to a critical stress state where deformation can start to occur, you start to basically damage the shear zone. You start to get kind of microcracks starting to form. Over time, those microcracks start to coalesce and form longer kind of cracks. Those cracks start to propagate. Eventually, those cracks are going to interact with each other, and eventually you're going to run away to failure because the strength of the material is dropping so quickly that it can't hold itself, and we get this acceleration. So I think it's a really good explanation of how we can get this time-dependent failure in certain conditions in brittle materials. So the next thing I want to talk about is the work we've been doing looking at slow-moving landslides. So this is an example that we've worked on over in New Zealand. This is the Undertook landslide complex in the North Island. So it's in a neogene kind of clay mudstone marine sediment. And these landslides, these translational landslides are kind of all across the northwest section of the North Island. And what we can see on the right-hand side is the displacement patterns that we see. So we see these periods of accelerated movement. We see these long periods of slow displacement, with these shorter periods where we've got these periods of acceleration. And if you look at the periods of acceleration, what you can see is that we can see the acceleration and deceleration relative to the pore pressure. And what we see is that basically as pore pressure is going up, you get a certain displacement rate response. As pore pressure is coming down, we get a different one. So it's basically telling us that in the landslide, deceleration starts with the pore pressure really high. So the pore pressure is actually higher as we start to decelerate, which is quite a strange concept when you think of effective stress. You'd expect that the pattern of movement would be linked to the pore pressure, but it seems that there's this kind of non-linear response. And work by Chris Massey kind of concluded that this must be kind of a structural control on the landslide that's responsible for this behavior. which might be the case. But if we look at other landslides, we see these patterns in other landslides as well. So you can see some landslides where the velocity, so the first one on the left is showing the depth of the groundwater level in this case against velocity, but it's basically showing that the rising pore water pressure and lowering pore pressure have the same velocity response. So that seems to be quite well connected. The next one along shows a landslide, much like the one that we're looking at, where we have, as the pore pressure is going, as the groundwater is going up, the velocity increases, but then it stays high as it comes down. And then on the final one, you can see that we've got the pore pressure going up the other way around. So landslides basically have this kind of non-linear behavior, and it's not clear as to why we get just these different styles of behavior. So this is something that we thought we could look at in the laboratory to see if it was kind of a laboratory-based thing, a mechanical thing. So this is the pattern of movement that we were looking at. So you can see on the left-hand side, we've got the displacement against time, and the pore pressure is the grey line, so the pore pressure going up and the pore pressure going down. And we ran an experiment in the laboratory trying to basically replicate the field. So the lab is the left-hand side, the right-hand side is the field. And you can see that we could replicate it pretty well in the lab. We got pretty good similar behavior to what we're seeing in the field if we push pore pressure up and pull it back down. So we were able to basically replicate the conditions quite well. And because of that, then we were able to look at things like what happens if we vary the pore pressure changes. So you can see on the top one, we've got a linear change in pore pressure, so pushing pore pressure up linearly and then pulling it down linearly over time. So we've got the acceleration and deceleration, and you can see we get the same pattern that we saw in the landslide. So as it's accelerating, the pore water pressure is lower than when it's decelerating. And then we thought, well, what happens if you vary the pore pressure change? If we have stepped pore pressure and we change the rate of pore pressure, how does that affect things? And you can see that we have these different steps, and when we do that, we get this interesting pattern, for example, here, where we push the pore pressure up and we get a change in displacement rate. And then when we hold that pore pressure constant, so we're not dropping it, we can see the displacement rate dropping off. And then as we start to increase the pore pressure again, it accelerates again. And then as we hold it the next time, it drops off. And as we pull it down, it drops really quickly, even though the pore pressure is higher. So the little graph on the right-hand side is our explanation for this. That we think that we have these two different concepts. We have the overall effect of the effective stress, which is driving one component of displacement, but there must be another effect which is to do with the rate of change of stress, which is also having an impact on the rate at which it's moving. So when both of those things are working together, that they're both positive, we obviously get a situation where the system is accelerating. Where we don't have a rate of change, we get a situation where it stays pretty much constant. And then when we have one negative, when we get the negative effect of pulling down the pore pressure, it means that it stops quite abruptly. So it seems that this is actually being controlled by the material properties. So the next thing I wanted to do was to look at what's happening in the landslide in relation to earthquakes. So this is in a seismically active area. We know that the landslide is moving over time. And we don't know how much of the displacement that we're seeing is due to water pressure, and we don't know how much of the displacement is due to rainfall events and due to rainfall, and we don't know how much is due to earthquakes. So we wanted to look at earthquakes, and we haven't really had any earthquakes in the monitoring record to be able to see how the landslide behaves. But we did have an understanding of large historical events. So we know that we've had PGAs of 0.94 meters per second, so magnitude 6.2 earthquakes. So we were able to basically set up experiments where we dynamically shake the material and look at basically during that shaking how far the slip occurs, how much movement occurs in the shear box. So what we're doing in these experiments is we're just basically dynamically changing the shear stress and measuring the strain response, and we're just changing the size of the shear stress change to try and understand what implications that has. So the graph here in the middle is just showing the distance. It's basically showing the shear stress, the maximum shear stress in each shape beyond the conventional failure envelope, the kind of monotonic failure envelope of the material. And what we found was if we plotted the normal distance from the failure envelope, so how much we've exceeded the failure envelope by, against the displacement rate, we've got this quite good trend through all our data. So it's kind of telling us that in an earthquake, basically it's the out of balance forces that are driving it. So once we exceed the failure envelope, it's the distance with which we exceed the failure envelope which is driving the speed at which it's moving. So then we looked at this in relation to actual modeling data. So the right-hand side is actually numerical modeling of the overall landslide. So we basically replotted this as strain, and we got a really good relationship between the way the landslide's moving and the way that we're getting movement to occur in the shear box. So yeah, so just to summarize this, it's basically saying that during periods of elevated pore pressure, the displacement rates seem to be influenced by both an absolute stress state component, which is basically driven by the normal effective stress that we're applying, and a transient state component, which is basically to do with the rate of change in normal effective stress, so this rate thing. During dynamic shear displacement, the rates are controlled by the extent by which the forces operating on the shear surface are out of balance, how much we kind of exceed the failure envelope. And once we kind of exceed the failure envelope, we move, and that rate is dictated by how much we exceed it. And then as soon as we go back, once the earthquake stops, the landslide basically stops moving. So we get these periods where it can accelerate and move. And the results suggest that if we look at the earthquake catalogue, compare the kind of return interval of rainfall against the return interval of large earthquakes, that most of the displacement that's occurring in the landslide is probably to do with rainfall, as opposed to do with earthquakes. So the earthquake certainly moves it, can move it quite far, but they're quite rare. So most of that movement is being controlled by the pore pressure and the way that the water is operating in the landslide. Move on to the next thing we looked at. So we started to look at submarine landslides, and one of the ones that we've been looking at is the Tahini landslide complex. And the interesting thing here is that obviously it's located on the active subduction zone, so it's sitting off the northeast coast of the North Island of New Zealand. But the really interesting thing about it is it's got a preserved morphology. So the little figure in the bottom right corner here of the main graph here is showing you the actual morphology of the landslide. So it's got these preserved blocks, which is quite unusual. Most of the big landslide systems on the subduction zone have disappeared, but this one's sitting there. So it's kind of suggesting that it's an active, slow-moving landslide. It's very much like a kind of terrestrial landslide that you'd expect to see, but obviously over a much bigger scale. And it's moving on a really low angle shear surface, like 2 to 6 degrees, kind of really low. And it's been, and luckily, because of its condition, it's basically been subject to multiple subsurface investigations. So people have been out drilling through this, so we actually are able to look through the core and actually look at the materials within it. But to date, most of the studies have really focused on non-seismic destabilizing factors, so things like the free gas in the system or fluids, those kind of things. No one's really looked at earthquakes, which is kind of strange because we're sitting on a subduction zone, and we know that this landslide must have experienced some pretty big earthquakes and must experience earthquakes regularly. So just from the earthquake catalogue, these are the kind of things that we know we were able to do, is to work out what kind of stress changes would have happened in certain earthquakes. So we've got the Kaikoura earthquake and what would have happened at the site there. We've got the Tiaro, magnitude 7.1. We've got the Gisborne earthquake, and then we've also been able to model, what the big subduction zone 8.3 earthquake would look like, and we've got an upper and lower limit. This is what that is. That's like a modeled one. So we kind of know that these are the kind of earthquakes that could be experienced. So the investigations have been done here. So we've got a really good understanding of the landslide. We know the kind of conditions. We've got several IODP drilling expeditions that have been here and got samples. So we've been able to basically be part of that and get samples from the IODP drilling and look at what they found in the investigation. And what they found was that, from this investigation, they're able to identify that the landslide, the base of the landslide debris is around 40 meters below the seafloor, that the landslide stratigraphy is largely dominated by these alternating mud and sand layers. And they also found these features that were kind of indicative of liquefaction in the sands. So this idea, if you've got this really low angle shear surface, perhaps what's happening is we're getting some kind of liquefaction behavior in the sands. And if you look at the actual sand grain size and things, it does look like it's it could be liquefiable. And the other really key thing during these investigations was they found that the hydrates were significantly deeper than the landslide, the base of the landslide. So all the ideas around triggering from free gas seem to be a lot less likely. The gas has got a long way to go, and it's got to move, it's got to migrate from depth, and then it's got to build up a pressure, and that pressure is not going to dissipate. So it's looking like the free gas is not a great explanation for this kind of slow-moving landslide. So we took those earthquakes that I showed you before. We created what the stress conditions would have been at the site. So we got some help with that to basically work out what the stress conditions were. And then we looked at different types of magnitude and duration shaking and looked at what happens to the material when we do that in an undrained system. So to create an undrained system, we basically control the volume of the sample in the machine so that the height doesn't change, it's fixed. If we control the volume of the material, it means that basically nothing can drain. And if it does drain, it means that we're going to change the normal effective stress by changing the normal stress rather than the pore pressure. And if we look at kind of liquefaction kind of work in the past, what they've shown is that that change in normal stress is basically the equivalent of the increased pore pressure. So we can use that to basically understand our effective stress change and think about that in terms of pore pressure. And what we found was that basically if we do short or long duration, low amplitude shaking, so like low stress changes, there's not sufficient, the shaking is not sufficient to generate any pore pressure, and it's not sufficient to cause any kind of deformation. So you can see here the shear displacement basically stays, it doesn't really change, so we don't get any kind of movement. If we do short duration, high amplitude shaking, we do start to generate pore pressure. And you can see this in the red kind of red line here. So we start to generate pore pressure, but the duration of shaking is not long enough to get us to the failure envelope. So we don't really mobilize the shear surface. We get a little bit of kind of strain response, but it's really quite minor. But if we have high amplitude, long duration ground shaking, we start to have time to build the pore pressure to reach the failure envelope. And as a consequence of that, we start to see the shear surface start to mobilize. And we can basically mobilize that shear surface while that effective stress is low enough. As soon as that effective stress starts to drop, as the shaking stops, obviously the normal effective stress increases back beyond the failure envelope and it stops. So we have quite a good explanation of how we could get this episodic movement on a low angle, sandy landslide shear surface without liquefaction that could explain why we've got this type of landslide in this location. I think I've just explained that, so I'll just move on. So another thing we've been interested in is more complex earthquake shaking. And one thing that's happened relatively recently in New Zealand is the Kaikoura earthquake. And during that, we've had this quite famous, well-written out now, canyon flushing event from the Kaikoura Canyon. Obviously, it's the longest coastal margin dispersal system on the Earth. And the earthquake basically had this full flushing event, which was like 850 million tons of sediment that was mobilized out of the canyon. So we have this huge loss of movement of sediment out of the canyon. But the interesting thing is that despite this, the coastal inundation during the earthquake wasn't that significant. There was coastal inundation, but basically it could be explained by the offshore fault displacements that occurred. It didn't need a big submarine landslide to explain it. So it says that the submarine landslides from this canyon were quite limited, but in reality, this is a big steep canyon with really soft sediments, and the expectation was that we would, a big earthquake with faults rupturing at the top of the canyon head would have created a big landslide. So we wanted to study this, and luckily, what had happened was NIWA had gone out and done surveying, bathymetric surveying quite recently before the earthquake. So they had a really good pre-survey of the canyon. And I think they were out at sea at the time of the earthquake, is that right? And so they realized what happened. So they went back to the canyon almost immediately afterwards and resurveyed the canyon. So we have this incredible pre and post bathymetry of the canyon that we've never been able to catch after a major earthquake. So we could see how the canyons changed. And there's been quite a few papers in the science and geology and things on some of the data that's come out of this. So we have a student over in Canterbury at the moment, Laura Ganesco, who's been working on this kind of from a geomorphological perspective. And what she really showed when she's mapping the changes is that most of the landslides are relatively shallow. So we have lots of these dispersed shallow landslides, and they're kind of poorly preserved debris flows and flow slides that have kind of come out of the canyon. And the sediment mobilized from the headscarp is only about 2% of the turbidity current. So the turbidity current seems to have obviously mobilized things deeper in the canyon. So it suggests that, the sediments really mobilized further down the canyon. So it's a really interesting question as to why we only got shallow landslides. And so again, we thought we could look at this in the laboratory, because the other thing they've done is during that first investigation, they'd actually taken cores from the canyon head. some of those pores were actually in locations where landslides happened. So we had intact samples at the right depth where the landslides occurred, which was kind of, again, really useful. So what we did this time was we said, well, can we actually replicate the exact, or as near as possible, the exact ground motions that went through the canyon, rather than simplify ground motions? So again, working with the seismologists, we worked out what the velocity acceleration was going in the vertical and horizontal. So we had a really big vertical component to the earthquake at this location. And then we've got the horizontal velocities as well. And because of the way the system works, we can control the horizontal and we can control the vertical. So we can put through the real earthquake wave in those two axes and basically see what happens and monitor how the shear surfaces form. So we did this, and we did this for the landslide that we knew had happened there, which was 15 meters below the seafloor, so quite a shallow system. And then we took 50 meters below the seafloor because we knew that was the depth of the sediment. So we knew that was where the kind of base of the sediment was before we hit the rock. So we took the two kind of, we took the where we knew, and we took where we knew we had a landslide and where we knew we hadn't. And we basically put this earthquake through. So figure A here is showing the grey. The grey is really what we programmed, and the black and the orange over the top is showing what actually happened in the experiment. And you can see in both cases the the experiment worked really well. So we were really able to actually kind of create that earthquake really quite well. I mean, it's not perfect, but it's not a bad representation. So the black is the 50 meters, and the orange is the 50 meters below seafloor. So C here is looking at what happened to the change in pore pressure, and D is the change in strain. That's the displacement of the shear surface. So what we can see is that in D, at 15 meters, we get to about just after 20 seconds, and the ground shaking is sufficient that we get really rapid acceleration and it slips. And we can't complete the test because it basically runs to the end of the shear box. We've got no more displacement, so it can't cut out and do anything else. When we did it at 50 meters, we basically don't see much deformation at all. And interestingly, in both cases, we only got a small real relative change in pore pressure, so about 25 kPa of pore pressure built up, despite the size of the ground shaking. So if we plot that as a stress in normal-effective stress shear stress space, again, against the conventional failure envelope for the material, which we do from static shear testing at different normal loads, we can see that at 50 meters below seafloor, during the earthquake, we greatly exceed the failure envelope, and at 50 meters, we don't exceed the failure envelope. So again, the grey is what we expected to happen from the experiment that we modeled to put in, and the orange is the actual case that we actually measured in the experiment. So what it's implying to me is that what's effectively happening here is the vertical components, the vertical loading is changing such that we're not getting that constant normal, constant volume that we'd expect in really undrained conditions potentially. So we're getting this big vertical acceleration and a big shear acceleration. So as a consequence of that, we're not generating the pore pressures that we'd expect. And actually then it becomes a case of we're controlling, the materials are being controlled effectively by whether they do or don't exceed the failure envelope. So a kind of really simple infinite slope model. So one of the things we looked at was, if we look at how the shear surface formed in that experiment, here we've got we're looking at basically how much, so this is the friction coefficient. So it's looking at the normal effective shear stress divided by the normal effective stress against the friction coefficient of the failure envelope. And what you can see is in the early part of the experiment, we don't create the friction coefficient, we don't exceed the friction coefficient. And then during the second stage, we do slightly exceed it, and we get some permanent deformation that we can see in the displacement time graph above, the strain time graph above. Again, in stage 3, we don't see any real deformation, and we don't exceed the friction coefficient. And then at about 18 seconds, we start to greatly exceed the friction coefficient regularly, and basically we slip very rapidly, and it slips away. So the next thing we did was we took all the landslides that we could find, and we looked at the depth and the position of the landslides. So we looked at the depth and the angle of the failure, the angle of the shear surface after the event. So we looked at how steep it was. And then again, we plotted this on the right-hand side in terms of its normal effective stress and the shear stress. And what we found was in nearly all the cases, the landslides were really close to the point of failure. So it's these shallow slopes that are really close to the failure envelope that when the earthquake came through, they exceeded and they failed. But there was only 2 that stood out, and they were kind of deeper ones. that had already exceeded the failure envelope. So it's a possibility that the deeper ones could be more complex geometry. It could be that we've got one material and we haven't really got a really good understanding of the kind of how the materials change. But we seem to have a really good explanation as to why you're going to get shallow landslides and no deep landslides during that earthquake. And again, it's a really interesting question then is, for me, is if the nature, the depth and the style of failure is controlled by the earthquake shaking, to what extent, when we look at kind of earthquake-induced landslides in the future, do we need to think more about the style of the earthquake and how the earthquake kind of stress path goes through the materials, as opposed to just thinking about how big the earthquake is and how long it lasts for? Because that could, if this is a factor we need to look at, that could really change the distribution, depth, style of landsliding depending on the kind of ground shaking that we experience. Again, I think I've talked that to death. So the next thing was really to move on to what we've been doing in the kind of fault movement space. So as I said before, I think it's really interesting, the physics that we're dealing with, and the kind of materials in landslides, they're kind of fine-grained sediments. A lot of them are on these kind of low-angled shear surfaces. We're interested in effective stress and stress changes. So the physics and things that are driving our landslides are very similar to what's going on in subduction zones. And during the Kaikoura earthquake, or after the Kaikoura earthquake, we had this period of unprecedented shallow slips event along the Huranga subduction zone. And these went on for weeks after the earthquake, and there were kind of delayed triggers and all these things. And so we thought this was really interesting. We knew we were going to be drilling through, the IODP was going to be drilling through the subduction zone. So we thought we could use our experimental approaches to basically look at, how do slow slip events and triggering of slow slip from dynamic shaking using our experiments. So I took some samples from IODP, and the two things I looked at were the hanging wall sediments, and I looked at the pelagic incoming plate sediments. And the first thing we did was look at basically if we slip it at a certain slip rate. So the slip rate we chose was basically the rate at which the plates are moving. If we control that slip rate and then move to a slow slip rate, so we measure the kind of friction coefficient of the material at the slow slip rate. And then if we put through strain controlled earthquakes, so we tell it how far to shake for a period of time, and then after the shaking is finished, we basically remeasure the friction coefficient at the slow slip rate and see if the friction coefficient is the same, higher or lower, and look at basically how the material behaved during the earthquake and then how it responded after. So on the left-hand side, you can see we've got the shear displacement that we're controlling. And then on the graphs on the right-hand side, we're looking at these two different dynamic 1 and dynamic 2 events. We're looking at the change in the friction coefficient through the dynamic shaking phase. And what you can see in the hanging wall is that as we start shaking, we have to exceed the conventional failure envelope for a couple of shakes. But basically, throughout the earthquake, friction coefficient gets lower, right, every time. If we look at the pelagic sediments, interestingly, we were able to produce some pore pressure in the pelagic sediments as we're shaking. But basically, the whole way through the earthquakes, we have to exceed the friction coefficient. So if you think about, rate dependency, it's kind of almost implying that at a higher rate, the pelagics are kind of strengthening, they're kind of velocity strengthening, and possibly the hanging wall is velocity weakening during the earthquake. But in both situations, afterwards, when we're measuring the friction coefficient, you can see that the friction coefficient is actually significantly higher, and we're getting as much higher kind of friction coefficients after each shake. Unfortunately, we couldn't do as many shakes on this one because we reached our maximum strain limits, so we only had a few of these. So that made me think around the concepts of like fault healing and whether we're getting some kind of behavior that's associated with healing, right? So the thing I did was take the pelagics and look at like a standard style healing test, but I did kind of really long holds. So the first hold is a kind of really quite a long one. So again, we're measuring the friction coefficient at the kind of plate rate, and then we hold the experiment still for a period of time, and then we basically move it at the slow slip rate. We measure the friction coefficient, and you can see that the longer we hold it for, the bigger the friction, the bigger the change in the friction coefficient is required, and we can plot that as friction coefficient against time, as you can do, and you can see that you get this kind of relationship that we expect. So one of the things I wondered about is what's happening to the density of the sample. How is it changing in volume? So I plotted the change in void ratio through both experiments. And what you can see is that the void ratio during dynamic loading changes significantly more than the void ratio in the static healing. So it seems like when we're shaking it, whether it's through the style of our experiment or whether it's the way the materials behave, we're basically densifying the sample and making it kind of stronger and stiffer. So it's basically like a stiffening from the dynamic loading. And we see that in earthquakes as well. We see that in places like Northridge, where you have these kind of compaction style landslides where you kind of get this stiffening of materials and you get compaction. So the next thing I wanted to do is look at this in a shear, a stress state condition. So this is the whole of this really long experiment. So initially we put a sample in, we shear it to create a shear surface at different shear rates. So we form a shear surface. Then we measure the shear stress required to move at the plate boundary rate. And then once we've measured that, we hold that shear stress. So we hold the shear stress at the kind of creep rate that we need to keep it creeping. And then from that shear stress, we then put through stress controlled earthquakes. So we're basically changing the friction coefficient, we're changing the stress that's being applied over a minute. And then after that, we're going back to the stress states that we expect the fault to be in. And we're looking to see if we basically generate any kind of slow slip or anything like that. So this went on for quite a long time. I did 28 dynamic cycles. And after a while, you can see that because nothing was really happening in the slow slip, I started to like incrementally load, try and say, okay, what happens in an earthquake if we actually end up with a slightly higher stress after the earthquake? See what happens. And you know, what we found was that we couldn't, in this material, the pelagic, we couldn't get kind of slow slip to occur. So we didn't see any slow slip. We saw, you know, movement that was way below the kind of, you know, what we'd expect, or even the plate boundary kind of slip rate. So regardless of the magnitude of the shaking, we just didn't get it to slip in those experiments. But what did happen that was quite interesting was at the end of the experiment, we measured the friction coefficient at the plate rate again by basically controlling the displacement rate, which is the blue dots. Let's look over here on the left-hand side. And then we held that stress state constant, that stress state constant, to keep measuring it. And what it did do after a period of time was it basically ran away to failure on its own. So now we've got a stress state which is below the dynamic stress states that we've applied during the earthquakes, significantly below, and possibly slightly above the slow slip rate that we saw. And the material somehow has basically decided that it's you know, something's happening, that it's basically decided to accelerate itself. So you can see here we've got displacement against time, and then we've got the displacement rate, and we're looking in the black box. We've taken that period of time before it basically catastrophically slips. And we've taken that to look at what's happening in the displacement patterns. And what you can see is you kind of get the primary, secondary, tertiary creep that we talked about in the kind of Barnes model, that kind of fracture propagation. If we plot that as 1 over velocity, you can see we get the kind of primary, secondary, and then the tertiary creep phase, which is what we see in landslides that are going to catastrophic fail. So I guess it's left me asking the question: is this a situation where we've got a material in the fault zone that, you know, over time as it loads, it doesn't slow slip, but this pelagic incoming plate sediment, if it's stressed enough, it will stiffen to a point where it could go through brittle failure. So could this be a place where you would have, you know, bigger subduction zone style earthquakes where you exceed that stress and can move quite quickly and have like more of a catastrophic kind of unstable slip? And just finally, go forward. So finally, the last thing I want to talk about was fault healing. So the fault healing was quite interesting to me. So I started to look at this in the hanging wall sediments. So this is kind of a set of standard healing experiments in two different sediments in the hanging wall. And again, we can see that we get this kind of linear, we get the same kind of trends that we'd expect, you know, with hold time. But I wanted to look at this, if we change that experiment to, rather than being strain control, if we made the slip happen with pore pressure. So if we push pore pressure into the fault and created slip, you know, how would that behave? Would that give us, you know, how would that happen if we basically episodically did that and looked at kind of healing with pore pressure? So a bit like the kind of seismic pumping concept from Simpson, you know, we basically push pore pressure in, we basically change the effective stress, we generate some slip, and then at a certain critical point, we basically stop that slip by putting the pore pressure back down, and we hold it for a period of time, and we push the pore pressure back up. So we're trying to see how the slip would evolve with pore pressure. So this is an experiment that I did. You can see each the blue is the pore pressure going up and then being pulled down quite abruptly. And you can see the kind of slip, the displacement, which we're controlling. We get to a certain point and we say, right, once you get to 3 millimeters or 2 millimeters or 1 millimeter, pull back the pore pressure really quickly and stop moving. We can see the kind of change in the dilation from normal displacement, so the kind of change in the height of the sample. So as we push pore pressure and we're dilating, and then as we pull the pore pressure down, we're getting kind of stiffening again. And the other thing I was interested in looking at is just how fast it's moving as we're pushing the pore pressure up, as we get some slip. So trying to work out the point at which we think we start to move really quickly. I was looking for the slow slip rate, which is still one microns a second, and looking at what was happening before it. So is it slipping quite quickly? Well, actually, if not, it's slipping really slowly. So it doesn't have a, it does seem to slip at a certain point. So we're not getting constant deformation. So we take this point and we start to look at that as the point at which it gives us the time at which we start to get our slow slip event, if that makes sense. So this is just looking at that experiment. The blue is the pore pressure one against the same sediment where we're doing a standard shear hold shear experiment. And if we plot this data, we can see that when we plot the change in friction coefficient against time, it's log time, the pore pressure experiments don't sit on the same line, they sit way off, which I thought was quite strange. Obviously, they're much longer experiments because it takes time for the pore pressure to build up. But so then I tried to look at this in kind of a stress path state where I looked at the normal effective stress, the shear stress. And if I plotted that, I took the friction coefficient and just plotted it higher up the graph. It seemed to me that I could pick up both of these and they make quite good sense in that, our stress path and the pore pressure is going kind of this way, to, horizontally, and our stress path is going up when we're changing the shear stress. So that said to me, actually, this fault healing, it might tell us something about what's actually controlling the fault healing, because it doesn't seem to be frictional, because the friction isn't actually changing. So it does suggest that what's changing is the cohesion. The cohesional strength is changing and the friction is staying the same. So I basically looked at the failure envelope and looked at a number of different parameters. So I looked at the change in normal effective stress. I looked at the normal distance from the failure envelope for each one. I looked at the change in cohesion and I looked at the change in the friction angle. And I basically plotted those against hold time and looked for the strongest relationship. The strongest relationship is effective stress, but we're actually controlling effective stress. So I'm not sure that that's appropriate. But apart from that, the strongest one is cohesion. So it looks to me that cohesion is the most likely explanation for why we're getting fault healing. So that was interesting to me coming from a landslide perspective, because if healing is not frictional, it's cohesional, it means it's going to have a much bigger effect at much shallower depths. As we get deeper, cohesion has there's no impact on depth of cohesion. That's going to have an impact on friction. So it says that healing and re-deep faults is not going to be very significant, but in shallow faults it could be quite significant, which means in landslides it could be very significant. And one of the things I've been looking at is the same kind of style of experiments, looking at landslides after the Kaikoura earthquake, trying to understand how they could reactivate, or how the landscape could reactivate after big earthquakes. And one of the things I was interested in was the big landslides that happened. So one of them was the Stanton landslide. And, the interest was, how would that reactivate if we got core fluids, back into the shear zone? Would it just creep along and be a kind of a management problem? Could it accelerate quickly? So here we've got 3 pore pressure periods where we've elevated the pore pressure. We've done the same thing. We started the slip moving and then we pulled the pore pressure down, and then we've had a longer hold period and then we pulled back up. And what came out from that was that the pattern of movement changed over time. And so the bottom graphs here, the first one is showing that asymptotic trend. And the second one, during 2 and 3, I had this, what we call an intermediate trend, which doesn't seem to be a strongly asymptotic, but not linear. And then finally, during 4, we got the linear trend. So if we look at those 3 patterns and we look at what happened in Viant, which is the Viant landslide disaster, which is above. So this is the patterns of movement in the Viant landslide. So the Viant landslide catastrophically failed in 1963, killing thousands of people in Italy. It actually moved for quite a long time beforehand, and people were measuring the patterns of movement. And you can see in the 60s, early 60s, it's an asymptotic trend. Over time, that changed to this intermediate trend. And at the time, the final kind of phase, it had this catastrophic failure. So it suggests to me that, if slip planes can heal, and sorry, also people have been started looking at the petrological analysis of this material from the Stanton, and they think they can show kind of healing in there as well, evidence that there's been fault healing previously before the earthquake, when there's been other landslides in that system. So it suggests to me that if we can get this healing, landslides may not respond the way we think, which is to expect them to keep moving in a certain way. And most of our landslide research tends to be on active landslide systems that are always kind of constantly creeping. We don't really look at ones that have been benign in the landscape for a long period of time because they can't move. But with climate change, there's a real concern that we're going to experience environmental conditions that these landslides haven't experienced for, for thousands of years. How would they respond if they've been able to heal? It might be that we don't see slow-moving landslides. We see catastrophic reactivations of landslides, and we really need to understand that in landslide systems. And just looking at the UK alone, we have a huge amount of coastal landslide systems that are really big, deep-seated landslide complexes. We've got things like Venda, where we've got people living on top of them. At the moment, they're slow-moving landslides, but with climate change, changes in the rainfall patterns, plus sea level change and changes at the coast, there's a real big question as to how could these systems reactivate these complex cliff systems, and what are the implications of that? So I just want to finally conclude, just to say advanced laboratory testing hopefully have shown us that, we can greatly improve our understanding of landslides and shallow fault movements. I think my results start to suggest that slip surfaces are complex, but they're significantly influenced by things like their material properties, the stress history, the rate and the application of stress, and their healing characteristics. And I really think that further studies that really start to combine these methodological approaches, from fault mechanics and landslide mechanics, which I don't think we've been that great at working across recently, historically, could really help to improve, our ability to forecast, the hazard posed by these kind of unstable slip phenomena in the future. That was it from me. Thank you very much.
Just going back to the ones that appear not to have any trigger.
Oh, yeah.
Is there any sense that those are particularly small landslips or large, or do they show wide range?
I think they tend to be large, and they tend to be in systems that can kind of get, like damage, so big rock slopes and, kind of over consolidated clays and those, but they tend to be the larger ones than shallow systems, I think, but that's an interesting question. I'm not, yeah, I mean, yeah.
It's completely the opposite way around.
Oh, okay.
I was thinking more like small.
Yeah, it's an interesting thing to look at. I haven't actually looked at that in depth, but most of the ones I'm aware of have been kind of deep-seated, but I guess they're the more exciting ones, so we might be missing some important ones.
Interesting. I guess I was interested in the sort of multidisciplinary side of your work. And
Yeah.
so you've shown a lot of experimental data and then sort of large scale observations. And I was wondering about how easy it is to connect between the lab analysis and the natural situations.
Yeah, I mean, I think it's quite hard. And I think in the landslide lab space, it's probably quite similar to the fault space in that you can't really scale, but you have to try and look at the patterns and how things are changing, and then look for the things that kind of link together. I think probably in the landslide space, the best way for us to do that is through numerical modeling. So, can I get that lab data? If it fits with the monitoring record, okay, that's one thing, but how does that work over a bigger system? Then having a good numerical model that can demonstrate that is the kind of the next step to move from kind of, a small sample to these big systems. But I guess it's a challenge to those scales are a big challenge. But I think the fact that we can show these mechanical processes at such a small scale and see them at such a large scale has got to be telling us that they've got to be pretty fundamentally important to driving them.